Right, so continuing with trig integrals, using the t results. So of course t being, if we represent tan x on 2, then sin x 2t on 1 plus t squared, cos x 1 minus t squared on 1 plus t squared. If we use that substitution, remember the substitution is t equals tan x on 2. Well then the t dx is a half sec squared x on 2, which becomes a half 1 plus tan squared, half 1 plus t squared. We end up with dx is 2 to t on 1 plus t squared. That's like another t result. You don't have to derive that each time. But if you do forget, then obviously just, we go through that differentiation process. That's where it comes from. But as I say, that's basically your t result for our substitution. So we get an integral like this. You see, we would like to have the derivative on top, but there's no way we're going to create sin x there. So we'll use our t results. So I'm going to use the substitution. T is tan x on 2, so dx will be 2 dt on 1 plus t squared. Subbing in, now the nice thing about that, remember we're going to be using these for substitution in the sine and cos mainly. And the denominator of sine and cos is 1 plus t squared. And the denominator of our dx is also 1 plus t squared. So we're always going to get lovely cancelling. So I can multiply top and bottom by 1 plus t squared, and I end up with a quadratic denominator. Now in this case I don't need to complete the square because it's just 13 plus t squared. So I know that's going to be inverse tan. So 2 on root 13, inverse tan of t on root 13. Now substitute the t back in. And there it is. Can't really tidy up that tan x on 2 on 13 on root 13. Remember, the x on 2 is inside the tan, so we can't push the 2 to the bottom of the fraction. It's just got to stay where it is. Now, I used it for tan x on 2. Of course, you can use it for other angles. Say I wanted to make t equal tan x. That's fine, but it does mean our substitution for dx will be different. So the t dx would become sec squared. I'd end up with the t on 1 plus t squared instead of 2 to t on 1 plus t squared. So to generalise that, if you're going to substitute t equals tan x on a, you will always end up with a to t on 1 plus t squared. So x on 3, 3 to t on 1 plus t squared, and so on. Ooh, look, they both got a. Okay, so there's a couple more out of 4G that specifically use the t results. So technique we use basically when we've got sines and coses and we can't resolve a derivative, and so how we're going to get rid of this.